joining us for our new Innovative Discovery series. So we are really thrilled today to have Dr. Gregory Dobler from University of Delaware to talk to us about his research using data science techniques for public health purposes. It's going to be fascinating, so I cannot wait. But before I introduce our speaker, please let me go over some housekeeping issues. So as you probably know, we will continue extending CME credits for our tech talks and our ID series presentations. We will distribute the information via email to those that registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Lisa Maturo at Christiane Care, and her email address is lisa.m.maturo@christianecare.org. Our next ID series will be on November 20th, and we'll have Dr. Jonathan Pertol from Drexel University, who will talk about policy dissemination and implementation research. So please do not miss also that presentation. And then we have a tech talk scheduled on December 3rd. And that will be Kimberly Carlson, who is a clinical researcher at Cerner Corporation, who will talk about Cerner Learning Health Network, overview of the Cerner real-world data. And it's really interesting for a lot of us because it's a new source of data that is available to Christiane Care investigators. So it will be on Thursday, December 3rd. So please do not miss this one also. So again, I'm really excited to introduce Dr. Dobler. Greg Dobler is assistant professor in the Biden School of Public Policy and Administration and in the Department of Physics and Astronomy at University of Delaware. He's also faculty in the Data Science Institute at University of Delaware. He obtained his PhD at University of Pennsylvania in Physics and Astronomy and did a postdoctoral fellowship at Harvard University as well as another fellowship at the very famous Kavli Institute for Theoretical Physics at University of California, Santa Barbara, focusing on astrophysics and on dark matter. Prior to his appointment at University of Delaware, he was director of the Urban Observatory at the Center of Urban Science, and he's still director, actually, I just learned. And it's so the Urban Observatory at NYU, where he and his team are doing amazing things, and you should really check their website. It's totally amazing. So currently, he and his team apply astrophysics techniques to study urban informatics using remote sensing, computer vision, machine learning, and data mining to study the interactions of the human, natural, and built components of the complex urban system. He had several grants as PI or co-PI from NSF and the Department of Energy. He has a long list of publications and is a teacher and a mentor, and we are extremely excited to have him giving us a talk today. So thank you so much. Great to be here with us.
Thank you, Claudia. That's a great introduction. Thank you very much. All right, so let's see. Let me share my screen again, since that was working. Start sharing the screen over here, and then all right. So hopefully everybody can see that. So right. So thanks for that great introduction. So as Claudine mentioned, I have a bit of a winding path through academia. I was a bona fide astrophysicist for about 10 years before making a 90-degree turn in my sort of research and career trajectory to start studying cities back in 2013. And there's a variety of reasons that I did that. And then when I got to I was in Santa Barbara, I moved to New York University to the Center for Urban Science and Progress, CUSP, there. And I started this facility called the Urban Observatory, where we use this remote imaging to study cities as complex systems, much in the same way that astronomers use remote imaging to study the universe. We developed a facility there to study cities as complex systems using remote imaging. That facility has now grown to be a a multi-city, multi-institutional facility, and we're in the process of sort of in the early stages of deploying also to Wilmington, Delaware. So hopefully there'll be an urban observatory for Wilmington soon. But that is not what I'm going to talk about today. I'm happy to do so more. If anybody has any questions about that, I can flip over to some other slides from other presentations and talk more about some of the work that we're doing there. But today I wanted to talk a bit about a few projects that are not specifically urban observatory related projects that I've been working on. Let's see. Back in 2013, when I sort of moved out of astronomy and into urban science, right, and into studying cities, there was several drivers for why I did that, but one of the drivers was really to sort of take the sort of skill set that I'd developed over my time in astrophysics to apply it to problems that had a bit more sort of real world impact, a bit more impact on people's lives. And so when I moved to NYU, I was building this observatory, but I was also sort of keeping my eye out for like, okay, the urban observatory is kind of like a very futuristic kind of thing, studying cities using remote imaging, pretty cool, but kind of futuristic. And so I continued sort of working on these projects that had sort of very sort of direct impact on people's lives that were more sort of classical data science kind of projects, and we'll talk a little bit more about what that sort of means. And often it was done in collaboration with public agencies in New York. So there were a lot of collaborations that were happening with the Center for Urban Science and Progress in New York City. And so there were a lot of collaborations that were being formed, and so I would get involved in these projects. And this was great because it really sort of, satisfied that urge to like take these sort of technical skills and put them to use in a specific context that could be helpful to people who are sort of running operations on the ground, important operations on the ground that were, keeping people healthy, making sure the city worked, making sure that services were delivered, and those kinds of things. So, like for example, I had a collaboration with the Department of Sanitation in New York. We were doing like predictions of waste generation and waste pickup using, some of the techniques I'll talk about in a minute. Had a long-standing collaboration with the Department of Parks and Recreation, and I will talk about one project that we worked on there today. And then sort of various collaborations on related projects with faculty around NYU also. Came down to the University of Delaware, and over the last, I've been here about almost 2 years now. I've been trying to keep up that sort of dual identity between this big urban observatory facility that I run, and then also these projects that have sort of direct impact on the community, right? So I'm going to talk about the latter today. In particular, I'm going to talk about a few projects that I've been working on. One with folks from Christiane Care at the Value Institute that are related to public health. And I'm going to put them in the context of machine learning. And so what I want to do today is I want to do a couple of things. I want to talk through those projects, but I also want to give a little bit of an introduction to sort of what machine learning is, and a couple of the models that are very common in machine learning, and in particular, one particular model that has seen a lot of success in multiple domains, including public health. And then we'll talk about as we go through that. So we're going to give a brief sort of rapid primer on machine learning, and then we're going to talk about a couple of projects I've been working on that apply some of those techniques. Feel free to interrupt me at any point and ask questions if you have any. Happy to answer questions as I go or answer questions at the end. Totally fine. If anything here, if you want to talk about anything here more, that you hear today more, this is my email address, gdobler@udel.edu. You can also find me on Twitter if you're a Twitter kind of person, at Gregory Dobler. Okay? All right. So what is machine learning? So this, for some folks in the audience, this may be old hat. For some folks, this may be totally new. So let's go through this a little bit and put in some definitions to make clear exactly what we're talking about. So very broadly, right, machine learning is any process by which a parameter in a model is algorithmically determined from data by a computer, right? So that's a bit of a mouthful, but basically what I mean here is you have data, and that data you want to perhaps make predictions about what you're going to find in the future. You perhaps want to figure out what that data tells you about maybe populations that you don't have data on, or areas that you don't have, like geographic areas in which you don't have data, right? And so that's sort of an interpolation kind of process, right? So you have this data, and so you want to model the data so that you can make essentially predictions somewhere, right? And so anytime that you write down a model for data, you have to have parameters in that model, right? If you're doing something like linear or logistic, well, let's talk about linear. If you have like linear regression, you have some scaling factor that relates one data variable with another variable, right? So that scaling factor, that slope, if you're going to fit a straight line to it, that is a parameter in your model. And so machine learning is a process by which you determine what those parameter values are algorithmically. And we'll talk a little bit about that in a minute. But it's essentially learning those parameter values from data, and you're doing it with a computer, with an algorithm. Okay? So what do I mean by determine? How do you actually do that? And here's where things start to get a little bit tricky. Determine in this context means that there's some objective metric, right? So if you're doing linear regression, something like a linear regression, then it's how much your model is different from the data, or sum of squares if you're into sum of squares, or R squared if you're a statistician and like R squared, right? So determine in this context means there's some objective metric that you need to optimize. Okay, and we'll talk about how we do something like that in the real world in some of these topics. Okay, that is to say, also, by the way, if you've ever fit a straight line to any data set ever, you've already sort of executed a machine learning task. So that's kind of the definition of machine learning. It's a very broad definition, and it encompasses a huge range of models that we'll talk about in a second. So now it's also true that the last, really 30 years, 20 to 30 years or so, there have been major advances in machine learning, major advances in the kinds of models that people build, and the way that people fit the parameters in those models, the way that people determine what the parameters are for a given data set. Now, sometimes these models are very complex. Sometimes they start off simple, but then become complex. Okay? So we're going to talk about a model exactly like that. And so the complexity in these models requires that you have a lot of data, and we'll see why in a minute. And so over the last 20 years, what's happened is there's been these advances in machine learning and machine learning technology, the way to learn how your model is describing data, plus the sort of data revolution that's happened, where there's just a massive influx of data of all kinds. In the public, I mean, just even in the sort of public health domain, even in the health domain, there's everything from like wearable devices to environment sensors in buildings, to large databases of health records, anonymized health records, just a huge explosion of data. Okay? Especially in fields like, for example, medical imaging, right, where there's just been a huge amount of data just dumped into dumped on people, because we can store data now, and we can compute very fast now because computers have gotten faster. And so combining these sort of machine learning advances with this data revolution, where we have all of this extra data, has really led to sort of revolutionary shifts in society at large, and also in individual domains, right? So the universe of these models, right, the sort of first piece of that equation, the universe of these models is very large, right? And we're not gonna go through a bunch, and everything on this sort of figure is not going to be, you're not going to get tested on it at the end of this, but sort of in sort of big buckets, right? There's things like classification. If I have a bunch of data, if I have data on things like has diabetes or doesn't have diabetes, and I have a bunch of I have a bunch of variables that are describing, say, a group of people and a bunch of people that have diabetes or don't have diabetes. And a new person comes in with those variables I can measure or maybe predict, classify whether or not that person has diabetes or not, right? So the classification tasks. That's as opposed to things like regression tasks where you're trying to predict a given value, trying to, say, maybe predict a blood pressure if you're in the sort of health sciences, right? There's a sort of different task which is related to clustering, which is I have a big data set and I want to try to find commonalities in the data set and assign sort of each individual if you're talking about people, or each car if you're talking about cars, or each geographic area if you're talking about geographic areas, assign each of those to a group that are sort of similar to each other, right? So sort of similarities between your data elements and sort of defining a metric that you can optimize that splits those into different subgroupings. I'll show an example of that in a second. And then dimensionality reduction is a little bit beyond the scope of what we're talking about, what we're going to talk about here, right? So these models, right? These models sort of, there's many examples of them. There's a whole lot you can read here. Some ones that may be sort of familiar to you if you're sort of in the sort of stats domain. Things like linear regression. So that's a machine learning model. Multilinear regression, you can sort of make that as complex as you want. Logistic regression, another model. Decision trees, right? So these models where you have a data set and you have a bunch of variables, and for a given data point, you have a bunch of variables, right? So if it's a person, they have a bunch of characteristics like height and weight and blood pressure and whatever, right? And you sort of start to partition that data set. Is blood pressure greater than some value? Yes. Less than some, or no. And then you have two subsets, and then you sort of slowly break apart those subsets. That's called a decision tree, essentially. And you can use that when you have a new, in the case of health sciences, when you have a new patient come in, sort of traverse the decision tree for the things you can measure and say, okay, well, this person is likely to have some condition, perhaps, right? On the clustering side, k-means clustering is very common. If you've never heard of it before, just to give a sort of a quick sort of picture about what that might look like, say you have data that has sort of two parameters that you can measure, and you have maybe 3, maybe 4 clusters, something like that here, right? And so k-means clustering basically assumes some number of clusters, k clusters. And then algorithmically, so from each of those clusters that it sort of randomly assigns, from each of those clusters, it sort of finds the distance of that cluster to all the elements of your data set, and then updates where that cluster center is based on the elements in your data set. Say if it's people and health, the elements of the number of people that are sort of closest to that cluster. So if you have something like height and weight, right? And so in this way, there's sort of this algorithmic process by which you're taking your data and you're starting to partition it automatically into subgroups, right? This can be very useful for sort of next level tasks like classification, and say, okay, well, if the folks in this group, if folks in this cluster characteristically have, some other say condition, then it's more likely that somebody who sort of the features that we can measure about them, height and weight, will also have that condition. Incidentally, this kind of thing is exactly how things are recommended to you on things like Netflix and Amazon, for example. You have a bunch of characteristics about you that places like Netflix and Amazon sort of group together with other viewers. And so when people watch something that they like, they then recommend it to you because you're sort of similar to that group of people. Okay? So there's a key difference between linear regression, logistic regression, and decision trees and k-means clustering, though, right? And that's the following. Supervised and unsupervised learning. So machine learning can be broken up into sort of 2 categories here. Supervised and unsupervised learning. What does it mean? Well, supervised learning means you have truth. You have some labeled data. You've measured a bunch of parameters, and you have labeled each of your data points as something, right? So in the case where we're talking about diabetes, you've measured height, weight, age, those kinds of things. And then you've labeled it, okay, that person has diabetes, that person does not, that person has diabetes, that person has diabetes, that person does not, right? So in supervised learning, you're using that labeled data, truth. You're using truth to build your model. You're comparing to truth. unsupervised learning, on the other hand, does not have truth, right? So over here, we weren't saying anything about whether or not these individuals actually had diabetes or not. We were just measuring their height and weight, right? And then sort of figuring out how do they group together, and then say, oh, well, let me look at this group over here. That ultimately gets determined by the algorithm. Do they characteristically have, say, diabetes more often than the groups over here, right? So in unsupervised learning, you're essentially learning structure in your data without ground truth. So there's pros and cons to both of those. What the examples that I'm going to show you in a minute, that are going to sort of make up the rest of the talk, are all going to be supervised learning examples. So the benefits of supervised learning are that you can generate highly specific, tailored models based on domain knowledge that you have, right? So if you are an expert in transportation, you can build a model that specifically incorporates characteristics of transportation. If you're an expert on public health, you can incorporate aspects of your model that are specific to public health or patient care or anything, right? You can build very highly specific and tailored models that you actually can sort of handcraft yourself. The negative of these kinds of models is that they require a lot of hand-labeled training data, right? So somebody actually has to go through and measure whether or not all those people have diabetes or not. And so that can take a really long time. And typically that's done by hand. And I'll give an example of a project in which that took the bulk of the time. For unsupervised learning, where you're basically just learning structure in your data, right? There's no need for labeled data, so that's a pro, right? That's the sort of the pattern recognition sort of happens automatically. But the problem is that there's no guarantee that the outputs actually describe the data in any useful or relevant way, right? So you can, for example, just to go back for a second, sorry. You can, for example, look at this and say, are there 3 clusters? Are there 4? Kind of hard to tell. Maybe there are 4. Then I group the individuals together and I sort of look at their outcomes in terms of having or not having diabetes. And maybe they're just 50-50 in each cluster, right? So just because you find groupings in your data doesn't mean that actually corresponds to something physical or useful. So that's the sort of downside of unsupervised learning. Okay? So let's talk about, so that was the sort of machine learning primer for the most part. We're going to talk about one more model. We're going to get pretty specific in a second on one more model. One that's sort of really revolutionized the field of machine learning, that's revolutionized the just technological fields left and right. And it's related to artificial intelligence and things like that. So here's an application of machine learning in healthcare that happened relatively recently that was pretty famous. So there was a group at Stanford that took a bunch of images of moles, right, on people's skin, and they built a machine learning model. And the goal of that model was to take input data, right, and we'll describe what's going on here in a second, train a model, but train, I mean like use data to fit parameters in a model, so that model could output whether or not that was a benign or malignant growth on skin, right? So this is there was sort of no extra input here. It's just, here's the picture, here's the output. Picture in is the picture of the mole, output is benign or malignant, right? And there's a great paper on this that Nature paper from a couple of years ago, very readable even for somebody like myself who is not a health expert. Right? And so one of the things they found, which was kind of incredible, so there's class of model they used is something called CNN. We'll talk about what that is in a minute. What they found that was kind of incredible was that using these CNNs actually outperforms the average dermatologist at skin cancer classification. Right? So just looking at the image, the model was able to classify. So there was ground truth, right? So it was known whether or not the lesions that the model was sort of trying to fit the data for, it was known whether or not those actually were benign or malignant. Right? And so once you trained up the model, it turned out that the accuracy of this model was a little bit just a little bit higher than for certain cases, a little bit higher than the average dermatologist who were looking at this. So that is not to say, obviously, and nobody, including the authors, argues that all of determination about whether or not a lesion is cancerous or not should be sort of offloaded onto a machine learning model. But this kind of discovery, this kind of advance in this sort of machine learning plus data, right? This kind of advance can lead to things like assisted diagnosis, right? Or additional information that a practitioner might be able to use for making determinations about a given situation. Okay. So what is this model exactly? And I want to talk about this for just a minute because we're about to jump into an example from my work where we used the model exactly like this. So this model used something called a neural network. So a neural network is made of this sort of construct called a neuron. In the sort of neural network literature, there's a little bit of inspiration taken from like neurons in the human brain, but mostly the metaphor doesn't stretch too far in general, right? But this is the sort of fundamental construct of what eventually becomes a neural network. This is an individual neuron here on the left. So what do these neurons in this models do, right? So they take input data, right? So these could be anything that you can measure. In the case, those we'll see in a second, in the case of the images, it's things like the brightness value or the color value in a given pixel. Perform some operation on them that we'll describe in a moment, and then output some number, right? So it's kind of like, just like a function. You take in some data and you spit out some number, okay? Now, the operation that it performs starts off as a linear operation. It just takes the data, weights the different data by some amount, combines it together, and just adds some offset called a bias, which is why it's referred to as B, right? So it calculates this number here, which is just all of your data. And the math is not important. We're not really going to talk about that more. But the basic idea here is you're taking your data, you're giving various weights to the different data that you're taking in, and then you're creating this number called Z. And then there's actually, this really doesn't matter at all. There's a sort of a transformation on that Z that happens if you're big into math kind of things. That transformation is called an activation function, where that Z is there's some function of that Z that happens. So it starts off with kind of like almost like with literally a linear weighting between your input data, and then has a nonlinear function that gets applied to that for your output, right? So it turns out that if you take one of these neurons and you start attaching it to other neurons, right? So this is just like that original. So this is your original data, like x1, x2, x3. So now here, rather than just having one neuron as an input, here we have 4 neurons as inputs, right? And each one of them is taking each of these data, right? And each one of them is applying its own weights to the different data. Each one of them has their own bias term too, right? And then each of the outputs of those goes to an output neuron. So that's taking the outputs as it's what the inputs of this output neuron are the outputs of this piece in the middle, right? So these neurons in the middle. And then it's sending an overall output of the whole model, right? So this is called the input layer. This is called the hidden layer. This is called the output layer. That's just a little bit of jargon. But the basic idea here is that you have this input data. There's a bunch of linear weightings and then nonlinear transformations that happen, and then another bunch of linear weightings and a nonlinear transformation that happens to an output. So it starts to get a little bit complex, right? So over in the last slide, it was pretty easy. We're weighting the inputs and then we have some output and it's all fine. But as you start to add more of them together, it starts to get very complex. And by the time you reach the output, it's a little bit hard to tell how each individual input is sort of contributing to the output. That's called a black box model. And so you can string a bunch of these together into what's called a deep neural network. And now it's sort of really going bananas, right? Now you have an awful lot of parameters. Each one of these, say, for example, has its own weight assigned to it. Each arrow has a weight. Each individual circle here has a bias, right? But you sort of start off on one side, and you send your data in, and all of these weightings happen, and then you come out the other side, and you sort of have two possibilities on the outside, right? And so what happens is you take a picture, and you put it through, and so these are like the pixel values that go as the input. All of these weightings happen. And then on the output, you have benign or malignant. Okay. So this is exactly how that model works that just was doing this great classification on whether or not a given lesion is cancerous or not. So now the trick is, we talked about machine learning before, fitting model parameters with data. So the trick from the machine learning point of view is all of those weights, every single W that would be in here, however you're weighting all of the input data and all of the outputs from those input data, those all have to be learned from ground truth, from many known examples. So the number of parameters in this model is absolutely enormous, right? So it's something like 1,000 parameters in this model, right? And so you need a lot of data, a tremendous amount of data, to be actually able to determine what the best weights are in each one of these arrows to give you the correct benign or malignant probability. So that process is called training a neural network. So this sort of model here is getting towards what's colloquially referred to as artificial intelligence these days. It says it's not actually from sort of computer science point of view. There's a lot that's related to things like information and control theory about what artificial intelligence actually is. But sort of in the sort of popular press these days, it's models like this one, very complex models that, it's hard to know exactly what's going on inside here, right? These are black box models. You can't tell. It's not like a decision tree. Oh, person is greater than this weight, less than this height, has diabetes, right? So that's a decision tree, very easy to see. Over here, a lot more difficult to see which pixels, for example, are the pixels that are contributing to whether or not this is benign or malignant, right? So this is getting towards the sort of AI that you often hear about in popular press, right? But the fundamental idea, right, all the math is not very important. The fundamental idea is that models like this are learning associations between points in your data, between data points, between like whether or not the pixel down here is bright and sort of pinkish, and whether or not the pixel up here is dark and sort of brownish. It's learning associations between data. Sometimes those associations may not be obvious to you as even perhaps an expert, right? Which is how these models sometimes perform, in some circumstances, perform a little bit better than humans. Right? There are other examples outside of sort of medicine where this is true too. Okay. So one last little fun thing that one can do with a convolutional neural network before we jump into the example one of the first example I want to talk about today. Right? So you can also do object detection with these. Turns out that these are really great detectors of objects and images, right? So there's a specific model, doesn't really matter what it means, but it's called an RCNN. The C stands for convolutional neural network. That convolution just is basically referring to the fact that these models find like features in things like edges in pictures or sort of changes in color in pictures, things like that, right? So this particular model, this RCNN model, is designed to detect objects and images. And so you take an input image like this, and as opposed to like classifying this as like, has a horse or has a dog or is outside, something like that, right? Some kind of binary classification actually finds individual objects in images, right? So this is a car, this is a dog, this is a horse, this is a person, this is a person. Sometimes it misses things, right? So it didn't get this horse over here, right? But that's the basic idea, is that you have a model that takes as an input an image and doesn't just classify the image, but actually finds objects within the image. Okay? So this model was, the sort of first instances of this model were being developed in 2013, 2014. It was really coming on the scene and becoming very, very popular for just how accurate it was at being able to find objects and images. Right? So that led myself and a couple of people to ask this question. What if we could use such a model where we're detecting objects and images to sort of find public-facing tobacco advertising? This was a project that I did with NYU student team. Started doing with an NYU student team a couple of years ago, and some collaborators up there at the time, Federica Bianco and Tom Kirshner at the School of Public Health up at NYU. Right. So we were, Tom and Federica and I were talking about like, oh, well, what are some of the fun things one can do with computer vision? And we're like, okay, well, what about tobacco advertising, right? So can we actually determine where there is tobacco advertising, right? So in particular, there's a huge corpus of images of public-facing tobacco advertising, right, in Google Street View, right? There's a huge data set sitting out there. Remember we talked about needing a lot of data to train these models because they have so many parameters, right? So the concept was, can we sort of go to the web and scrape a bunch of this Google Street View imaging, apply some of these models that find objects and images, train the model to not find dogs or horses or people or cars, but to find tobacco advertising, point-of-sale tobacco advertising, right? And then once we could do that, then the question is, okay, well, can you correlate that with things like geographic distributions of health outcomes from tobacco-related illness, right? Or can you sort of take where that advertising is and look at things like bus routes to schools or something like that? So that was the task that we set out on. And so we wanted to start doing this in New York City at the time, right? So the way to generate, remember we said, okay, well, doing that distinction between is cancerous, is not cancerous for those skin lesions, right? The way to actually do that is you have to have a bunch of hand-labeled ground truth. You have to have a bunch of images of skin lesions that you know are either benign or malignant, right? So in this case, we needed a bunch of examples of images that were cigarette signs or tobacco signs or were not tobacco signs, right? So how do you actually do that? You don't just want to start clicking through Google Street View to try to find pictures of tobacco signs. Yeah, it will take you a very, very long time, and you can grow very old doing that by hand. So what we wanted to do is we wanted to increase the probability that a Google Street View image would have a tobacco sign so that we could then take it and label it as that's a tobacco sign. So you go and you grab where all of the licensed vendors are in New York, and there's about just over 10,000 licensed vendors in New York, right? And then you go to Google Street View. So here's an image from the address of one of the licensed vendors in New York. And you can see that this is the licensed vendor. You can see that there is tobacco advertising in this image. And it's a little bit more complex because, this is a picture out the front of the car, right? But there's a full 360 panorama, and you want to check all of that. So each of these 10,000 vendors has 4 images associated with it. It turns out that Google Street View, you can specify how you do it, but it's sort of easiest to break it up into the full panorama into 4 images, right? And so those 10,000 known vendor addresses are actually something like 40,000 Google Street View images. And so remember the con in the supervised learning process, the negative attribute of that was that you had to go in and hand label a bunch of data, right? You had to go in and actually generate truth. In the case of the benign or malignant skin lesions, you actually had to go and measure whether or not it was benign or malignant before you could actually apply the model. So we went to, say, for example, the first image, and by hand said, there you go, those are examples of tobacco signs. And we do that many, 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 many times, and you get a huge training set on which to train your model. Now, it turns out to be maybe not quite big enough. There are so many parameters in the model, it turns out to be quite big enough. So we do what's called training set enhancement, where you take one image that has tobacco signs in it, and you modify the colors a bit, you modify the contrast a little bit, you modify the brightness a little bit, right? So things that might occur naturally so that you can generate sort of new data that is sort of different than your old data. You have to be very careful about how you actually train a model on that. A lot of sort of technical details on that front that we won't go into, but you can enhance training sets that way to sort of boost the accuracy of your model. Then we went in, In the end, we had about 1,000 training examples. And so then we went in. So these are examples of the model being run in practice. So you can see these are true positives. These are examples where we were successful at finding tobacco advertising in the image. Right? And here's another one. Here's another one. Sometimes you can see, sometimes the signs are close and they're sort of high resolution. Sometimes the signs are far away and they're sort of lower resolution. But here's the model actually successfully finding examples of tobacco advertising. There were some false positives too, right? Things like street signs, other street signs that maybe the sort of Second Avenue sign up here kind of looks like a Newport sign at a distance. I don't know. Road markers maybe look like a picture of a cigarette, perhaps, or sometimes it's kind of hard to tell exactly what's going on. But there are false positives also, and so you can sort of figure out why your model's failing and potentially deal with that. But in the end, we then went through all census block groups in New York City, grabbed all the Google Street View data from the whole city and not just the vendors, and then applied that model to the whole city, so that you can say, at a given location, is there a tobacco sign? And you get maps that look like this one, where there's sort of high density of tobacco advertising in sort of mid and lower Manhattan, up here towards Harlem and into the Bronx, and over here towards the boundary between Brooklyn and Queens. Turns out that the tobacco advertising happens to be just sort of spatially correlated with the socioeconomic and demographic characteristics of the population. But you could also, ask other questions like, okay, well, where's the map of vendors? Here's the map of vendors. So how much advertising is there in areas where there actually aren't even any vendors, right? So that's something else one could do. So that's that project. So last year we were awarded an INBRI award to do this, to sort of move this technology down to Delaware now, do for the whole state of Delaware. So we're in the process of doing that. In particular, one of the great things, remember in the beginning we said we want to sort of identify where this point of sale advertising is, and then we want to ask questions like, okay, how does that correlate with public health outcomes? So at the Biden School, there's the Center for Community Research and Service, which has direct access to Medicaid data, right? And so we're in the process of aggregating Medicaid data and then combining, and then for the purpose of then combining with things like the amount of tobacco advertising in a given area. So that's that project. And now I'm going to switch gears a little bit, but we're going to sort of keep the same methodological approach, but we're going to talk about something a little bit different. So I mentioned in the beginning I had a long-standing collaboration with the New York City Department of Parks and Recreation, right? So New York State Department of Parks and Recreation is sort of responsible for the largest acreage of property in all of New York City, 30,000 acres of land, 5,000 properties, 800 athletic fields, and so on and so forth. So it's a huge agency within New York City. It's very much on the mind of both policy folks and folks who live in the city, right? And there's this whole issue of things like equitable distribution of resources and equitable distribution of green spaces. And as we'll talk about in a minute, that has a public health dimension as well, right? And there's this great quote from Bill de Blasio that every New Yorker deserves access to clean, safe green spaces, no matter what neighborhood they live in. And so I had a multi-year project that was going on with New York City DPR, Department of Parks and Recreation, that was looking at using inspection data from parks to sort of predict where parks might start failing in the future, areas that might need additional resources to get their inspection rates up. But another one we did was related to public health. So benefits of urban green spaces, right? So it promotes physical activity and public health, psychological impacts with the increased biodiversity. It alleviates congestion and pollution and noise, all things that negatively impact public health, right? There's been a lot of work on things like the access to green spaces and how people might use green spaces. So there's a great study in Europe showing the sort of change as you go from sort of northern to southern Europe in the access and the availability of public green spaces to the local population, right? So, Department of Parks and Recreation, we were working on this project. We were looking at these park inspections and whether or not their parks are failing inspections or not. And one of these conversations we had, I was like, so what are some of the big challenges you face? And the one of the big ones that they talked about was we have no idea who uses our parks, how often they use it. We have no idea how our parks get used, if they get used at all. So what we do is we send out volunteers, right, and sort of strategically during summer months or something like that to go take surveys. But that's just one point in time. They go out for an afternoon and they talk to people and they count them, do a head count of folks in the park at the time. But they don't really have an estimate for utilization over time, right? They don't know which amenities are used most often. Park benches are used, or playgrounds used, what? How long do folks stay within a park? Are they walking their dog? Are they riding their bike? Those kinds of things. This is just information they don't have, right? So much like with the Google Street View image case, right? So we started talking about, okay, well, what if you had what if you didn't have a human observer go in there to like record what was going on at the time, but what if you had a sort of more continuous observer? In particular, what if you sort of sighted a little stop motion camera near the sort of low resolution stop motion camera sort of overlooking the park so that you could get a sort of sense of how things were going, right? So these kinds of imaging devices are all over the place for things like Department of Transportation or the various law enforcement agencies. But what if you, as the park department, just put up a little, not talking about like a big camera network, but a little stop motion camera for a week or something like that, just to get a sense of how parks were being used. So I said, okay, let's try a pilot. So we got a couple of these sort of Brno stop motion cameras. We mounted them, they mounted them, at a couple of parks in Brooklyn that were sort of test cases for how something like this might work. And this is the kind of imaging you get out. Very low resolution imaging. There's nothing, it's not even close to possible to do face recognition or anything like that, right? So there's no personally identifiable information being collected. The frame rates are very low, right? And so we had these images in these different parks. And the idea was, okay, can we use the same sort of techniques that we used in the tobacco sign case to detect humans in parks, right? So that's a human, that's a human, that's a human. And then because everything is sort of time stamped and there's a time being collected as well, do things like look at usage over time in a given park. Okay? So there were a couple of, as with all of these kinds of things, so I deploy imaging devices for a living, and there are always complications. Some things like the camera angle changing periodically as the cherry picker goes up and the person swaps out the memory card because it fills up after a couple of days. It kind of bumps the camera a bit and it moves direction, and so those kinds of things one has to take into consideration. But in the end, we get something like this. Okay, so over here it's going to be a time lapse. Over here is the stop motion video. Over here is a machine learning model generated background image. So it's taking the things that are not changing. This is an image of everything that's constant. Down here on the left is going to be that original image minus that constant background. And over here on the right is a little post-processing done to detect where there are changes happening. And so we get things like this. So we get these, sometimes you get detections of things like, trees blowing, leaves blowing in trees and then shadows on the ground. But for the most part, we're getting sort of usage of things like the playground equipment here, the bench equipment when somebody goes over and sits down on the bench, folks walking by the park and so on and so forth, okay? So we can take that and then we can then say, okay, well, how are we doing, right? So look over here when we sort of count up the number of detections, it's low. We look at the image, there's nobody there. We can count up the number of folks in the image. It turns out that the numbers that are on the top actually are the number of people in the image. We can figure out sort of where that detection is happening, right? So on the bench or on the play equipment, etc. And then we can look at time series, the number of users in the park over time. And you look at these time series and you say, oh, there's a bunch of users here. Then they go away, a bunch of users here, then they go away, a bunch of users here, then they go away. A whole lot of nothing for a while, a last couple of bumps of users towards the end of the day, and then nothing in the evening, right? So when it turns out that if you go actually look at where this park is located, there's a school right across the street, and this public park was being used as sort of a recess playground for the school that was across the street because they didn't have one, right? So you can see this is sort of recess, letting out, going back into school, letting out, going back in, letting out for the day. Things sort of this sort of process here ends right around 3 o'clock, right around the end of the school day. Then a whole lot of nothing happens in that park, not a whole lot of utilization for the rest of the day until the early evening, right? So just after dinner-ish. right? So just after 6 p.m., a little bit of extra activity before it turns dark. Okay. All right, so we're doing all these projects. The last one I want to mention, and I'll talk about this pretty quickly. I know there are some folks on the call who are actually involved in this project. Last one I want to talk about really quickly is related to an email that I got back on March 29th of this year. So the message came from Christiane Care, Value Institute, and also the Delaware Emergency Management Agency to the Biden School faculty. So I'm, going along, doing this urban observatory project, doing these things, right? And we get an email. The email says, can we adopt CHIME to make predictions for COVID that are specific to Delaware hospital demand? And I had absolutely no idea what CHIME was. Turns out that CHIME is a disease-spreading modeling software written in Python coding language, right? And so this Python coding language is a sort of a language for writing computer code. It's what I write all of these models. I build all of these in Python. All my students do as well too, right? So we're sort of well-versed in Python in my research group. And said, okay, yeah, I can write Python code, but I know absolutely nothing about disease spread. I'm as freaked out as everybody else is what's going on, and I don't really have any insight as to the sort of epidemiological piece of that. Fair enough, right? The email came through Eric Best, who's currently at who's at Penn State now, was at the Biden School at the time in the Center for Applied Demography and Survey Research, and so he sent an email around to me and Federica. Saying, hey, you guys are good with Python. There's been this sort of semi-urgent request for some Python expertise so that they can use this CHIME, this publicly available code to predict hospital beds, what hospital beds are going to be needed over the next coming weeks, right? So that actually came in from Mia Papas and Sichiam, who are on this call right now, I think. Kind of hard to see. There's a bunch of little squares right now, but I think I saw them earlier. And AJ Shaw from the Delaware Emergency Management Agency, right? So this was, there was sort of a big effort going on to do capacity planning in the early days as cases were sort of going up and up, and so what can we expect out of this, right? And so, not being an epidemiologist, I can't interpret any of that data, but I can sort of work with the sort of tools of that to provide things like, okay, if I have a publicly available software, can I sort of adapt that to Delaware? Okay, so this is that model built by some Code for Philly folks in association with the University of Pennsylvania. It employs this SIR, this susceptible, infected, and recovered model, where you have a population that goes from being susceptible to infected to recovered. Various characteristics. It's a simulation, so it starts with a single infected individual. Then sort of through given time steps, takes a fraction of that population, moves them into infected, and then moves them into recovered. Some of the parameters in the model include things like how the doubling time of the disease, social distancing, how much social distancing might impact that, a constant social distancing, hospitalization rate, length of stay, et cetera, right? And so we took that and we made a bunch of these predictions. And so these spaghetti plots it's 15,000 different simulations of what could have possibly happened starting on that day and then going forward 3 months, going forward about 3 months into the future, right? And so the question was, okay, which of these curves are we actually on in the early days? And so these kinds of sort of simulations were being used to say, okay, well, looks like we're kind of lying along this curve, so here's what we can expect over time, right? But there were a bunch of issues related to things like how do policy changes. In the early days, it was simple to model in a way, in that the disease was kind of unchecked, spreading like wildfire through some of the communities on the coast, right? And so things were very mathematically kind of stable, but then things started getting put in that were kind of altering the trajectory of the disease away from the sort of simple susceptible to infected recovered kind of spread here. Policy changes, right? So how do policy changes, things like closings and stuff, right? What about suppression of disease in summer months at the time? Right. What about demographic distributions? How does that matter, right? Because older folks were being affected more than younger folks, right? And there's big demographic changes in different parts of the state, and so you're going to potentially get very different demand in different hospitals in different locations, right? What about behavioral properties of both the in and out of state populations? What about the resurgence in the winter, which seems that it's coming up on us now? It seems that we're right in it. And then what about reinfection? So once people are recovered, this is still a big question, and still is today, right? So we developed this new model, and this is the sort of last thing I'll say today. We developed this new model called DHARMA, stands for Delaware Health and Recovery Metrics Analysis, where we're sort of keeping track of, rather than sort of looking at the population as a whole, we're simulating each individual within the population, right? And sort of progressing each one of those through a disease. So on the first day, a single infected individual infects 3 folks. They go through a disease progression where they're asymptomatic and then symptomatic. Sometimes they go to the hospital, right? And then on the next day, those folks infect another set of folks. They go through their disease progression, and so on and so forth. And so in the end, we wind up with sort of each individual over 180 days in a simulation. And we can sort of add up down each of these columns to give us the number of asymptomatic, symptomatic, or hospitalized folks on a given day. And this model is very flexible. It allows us to incorporate things like time-dependent social distancing. So since we're following sort of each individual in the simulation, we can sort of assign them whether or not they're social distancing. We can assign them a probability of wearing a mask or their person-to-person contact rates, right? We can assign each individual certain demographic or even socioeconomic characteristics, right? So these are they a essential worker? Do they need to be? Are they more likely to get infected because they're an essential worker? The length of stay in the hospital can be adjusted for each individual, so on and so forth. So behavioral changes, demographic characteristics, disease characteristics, right? Things like asymptomatic subpopulations or vaccine availability. But then also policy changes, openings and closings, hospital discharge and intakes operations. Right? And so in the end, what we do nowadays, right, so this has now been going on for 6 months, great collaboration that we've had. What we do nowadays is that we produce models that look like this, right? So we produce huge suites of models that all kind of fit the data. And then we can say, okay, well, how does something like the amount of hospitalized, the fraction of folks who go to the hospital, how does that sort of impact the simulation in terms of whether or not people are social distancing, right? And so what does the sort of future outcome look like there? What are the sort of covariances between those two parameters? And so these models are being sort of put to direct use by area hospitals in Delaware for things like operations and capacity planning. I will stop there. Happy to take any questions. This is my email address, and this is me on Twitter if there's anything else you want to hear about.
Thank you so much, Greg. This was just fascinating. I mean, I could listen to you all day. I would love to have even more details about the current project with the Delaware data. I think there are some questions in the chat. If you have access to it, if you don't mind looking.
Let me see if I have access to the.
I can read the questions.
Not sure. Oh, there it is. Okay, sure. Is an analogy for supervised, unsupervised the difference between conformity and exploratory factor analysis? In a way, yes, though it's also the case that you can have you can sort of explore your data knowing ground truth as well, right? So I would maybe phrase it a bit more as like unsupervised learning is you're trying to discover patterns in data, right? You're trying to discover patterns in data without sort of imposing knowledge about what the outcome should be. Now, you still have to parameterize your model. So you're saying, hey, there have to be 4 clusters here, not 3, right? So that's still something you have to assign, right? But it's a bit more like automatic pattern recognition. And just, there's the holy grail in sort of machine learning is to be able to do automatic pattern recognition while also telling you something important about your data. And so it's sort of combining the outcomes of supervised learning with the sort of techniques of unsupervised learning. That's an active area of research in machine learning. Yes, hopefully that answered. We're here, we talk. Curious if you use TensorFlow for your neural network models or some other package. We're using TensorFlow to build speech models in our lab. Yeah, I use TensorFlow for. So we're using TensorFlow for the COVID project. We used but are porting over to TensorFlow. We originally did the tobacco sign detection in PyTorch. But we're porting over to TensorFlow now. PyTorch has some nice properties that are sort of for folks who are not familiar with not familiar with sort of neural network sort of software. It's a little bit more familiar to sort of standard Python kind of stuff. TensorFlow is a little bit sort of higher level kind of thing. So the students that were working on it weren't quite familiar with TensorFlow, so we started with PyTorch. There's always this, there's a big competition between TensorFlow and PyTorch. I like TensorFlow, but yeah. Is it possible to use satellite imagery? Hopefully I didn't miss anything. Is it possible to use satellite imagery to get a sense of population movement during the time of COVID and associate that with rates of increase in specific areas? So yes and no. So satellite imagery is one of the issues with satellite imagery is that it's very, there's a long time in between observations, typically a few days or something like that, right? There's a push using things called CubeSats. They're these little satellites that folks are trying to build hundreds of them to fly around and sort of take imaging and updating once every 15 minutes or something. But at the moment, it's at most a day, at least a day usually between observations. So, and the resolution of satellites is characteristically quite small. However, if you get high resolution imaging, you could do things like look at, are there cars parked in like driveways and the beaches where there weren't before, people sort of leaving the urban areas and going to their vacation homes or something, I don't know. But there's been a lot of discussion. In fact, I have another project going on to talk about right here, where we're using large-scale traffic camera networks to sort of scrape a bunch of traffic camera images and then look at the number of folks on the street as a function of time, or the number of cars going down the street on a function of time to give you a sense of human mobility. And that actually you can get that kind of information. Are people out on the street? Are they moving around or are they not, right? So if you have a large sort of street-level camera network, you can do that as well. And I think would be fascinating to do this with parks during COVID-19. Yeah, absolutely. So so that's related to what I just talked about before. Some of the street camera networks that we're looking at do have imaging right near public parks, particularly things like Central Park and stuff like that in New York. So yeah, stay tuned for that one. And I think that's all.
Any other questions? Oh, Greg? That's all.
No
All
more
right.
questions, but this is me. I just want to say that, first of all, great talk, and it has really been a great collaboration, and it has been, I think part of the way we found each other was through the CTR. So talks like this and kind of building that network and collaborating across institutions, which, is what we all need in times of crisis and in times of not crisis, but it's been great.
Absolutely. So from my, first of all, yes, amazing collaboration. It's been wonderful, absolutely incredible working with you all. There's a lot of discussion in the sort of communities that are outside of public health, saying, okay, well, maybe we shouldn't parachute into something, right? And sort of, just jump in and be like, oh, I can solve COVID, right? No, when you know nothing about it, right? And you're not an epidemiologist. And so, but where these kinds of collaborations, I think, really are great, are sort of smaller areas or areas where there are not sort of huge amounts of resources of like a bajillion technical experts all over the place, right? So, somebody who's simultaneously a genius technical expert and a genius epidemiologist, right? So sometimes, in the sort of smaller places, smaller states like Delaware compared to things like New York or California or something like that, right? You can make these very nimble collaborations that have potential for huge impact. And I mean, credit to Eric Best here. He was able to like get a bunch of data sharing agreements in order with all the DE hospitals, lickety split. And so we were actually able to get data and start fitting data very fast, right? And so that kind of thing, I think, is not even possible in sort of larger areas where there's so much more complexity. But having a bunch of people who are open-minded and very enthusiastic has been really wonderful.
So do you think that so do you run your model like every day with the data that you receive every day, or is it weekly or?
Yeah,
daily?
we run our model. We have. I was a little bit glib. We actually have a couple of tiers of models. Some of them are very fast and can be run sort of easily every day. They could be run every minute, some of them. Some of them take many hours to run. So these very large-scale simulations that include lots of different flexibility in them can sometimes take up to a day or more to run. And so the fast models we definitely do every day. Some of the larger models we do every couple of days. But we make predictions every day, and our group pushes out predictions to all Delaware hospitals every day. Say, here's
that was my next question.
Yeah, here's our prediction for the next 10 days. Eric Best sends out an email through DEMA every day to every hospital in the state saying, here's what our group is predicting for the next 10 days or something.
So how does the prediction meet the reality?
So far, pretty good.
They're good.
Yeah.
For Christiane Care, they're definitely good. We send it out wide weekly instead of daily, but we get it daily. But they've been really good.
Yeah, and so we were just talking a couple of days ago about how we might need to make some model adjustments because we are seeing an increase right now, and so the data is kind of like on the edge of where our models were predicting before, and so we need to make some model adjustments, maybe make some changes to things like contact rates or temperature-dependent changes in the disease or things like that, right?
So will you add the vaccination rates or vaccination when it comes up? Or?
Absolutely. We've had a lot of conversations about that one, and it's not at all straightforward how that's going to happen, right? So things like vaccinating a given area, you have to include like the fact you have to include the extreme complexity in the distribution mechanisms that are going to happen, right? And so it's not just going to be, and this is where those sort of simple models like CHIME, where they have this single population level model, are just, they can't handle anything like this, right? Like you can't just say, okay, we're going to vaccinate 20% of the population, right? Mia just posted in the chat. Yeah, C has been talking a lot to us about this and making sure that we sort of are thinking about this in our modeling. You can't just say, okay, let's vaccinate 20% of the population and see what happens, because those 20% are geographically in disparate places. They have different contact rates between sort of young and old, younger folks and older folks. I mean, it's not a population level thing. So incorporating all those complexities in the distribution, including the time dependence, the plan is to do that. And I'd like to get to a place where we can say, okay, well, if we vaccinate X% of the population and we open up bars but not the university, then here's what we predict for next week, kind of thing, right? So that's where we're sort of shooting for over the next several months to a year.
And I'm sorry, I still have questions. I guess we had 1 7. Just last question. Did you include also the reopening of the schools in your model?
We did. So the way that we are including this in the model right now is through changes in the contact rate, right? So the relative contact rate among subpopulations. And so our models actually require a change in the contact rate right around the time that University of Delaware it didn't open, but more students were coming to campus right around the September time. So our model was not fitting unless we included that increased contact rate in Newcastle around that time.
Right. Well, this is really fascinating. You'll have to come back, Greg. I think we need to schedule you sometimes in the spring, early spring.
Happy to do it. Very happy to talk to you all.
Great. Thank you so much. Thank you so much, everyone.
It's been wonderful. Let me know. You can send me an email, anybody, if you have any other questions.
All right. Bye.
Take care. Bye-bye.
Bye.